Hello, and welcome back to Physics 141 Classical Electromagnetism 1. So let's first review what we have discussed in the previous lessons before we start this lesson. So we have encountered Laplace equation before in spherical coordinates. So if your potential is a function of r, theta, and phi, then this is your Laplace equation in spherical coordinates. But since the Laplacian is equal to 0, then we can multiply both sides by r squared sine theta to further simplify our Laplace equation. So this will now be our Laplace equation in spherical coordinates. We also have encountered the Laplace equation in cylindrical coordinates, where our potential now will be a function of s, phi, and z. And we also have discussed before about the electric potential at point r with respect to a reference point. So it's just basically the integral, a negative integral of E dot dl. So given the electric field, it's just a dl here is just the path from the reference point to the point r. So I don't know if you have encountered Legendre polynomials, but you should have encountered this in your mathematical physics, but maybe due to pandemic reasons you have not approach or have gotten up to this topic yet in mathematical physics. But I'm just gonna introduce some of the Legendre polynomials here. So the Legendre polynomials are of the functions of PLX. PL of x is equal to 1 is 1, and the P sub 0 when L is equal to 0, so P0 of x is 1, and when L is equal to 1, P1 x is x, and so on. These are just the up to L is equal to 3 Legendre polynomials. In this lesson, our x here will be cosine theta. So meaning P0 of cosine theta is 1. So you can actually write 1, the number 1, as a Legendre polynomial P0 of x or P0 of cosine theta. And P1 of x, if x is equal to cosine theta, P1 of cosine theta will be cosine theta. So you can actually cosine theta as P1. So 1 will be P0, cosine theta will be P1, and if you have 3 cosine squared theta minus 1 over 2, that is actually P2 in terms of Legendre polynomials. And if you have 5 cosine cubed theta minus 3 cosine theta over 2, that's actually the P3 of cosine theta na Legendre polynomial. So this lesson will be a continuation of the separation of variables na lesson, and we will now show how to do it in spherical and cylindrical coordinates. So of course the generic idea of how to use the separation of variables technique is already presented to you in the previous lesson. So we will just use the same approach but now in a different coordinate system. So let's now start the lesson. So when you do separation of variables in spherical coordinates, so we start with the Laplace equation in spherical coordinates, and to make our lives easier we will make some assumption. So we will not be delving into the three-dimensional Laplace equation, because most of the time spherical symmetry has what we call an azimuthal symmetry. So the azimuthal angle phi is actually has a symmetry along the phi direction. So if this is your sphere, the potential will actually most of the time be the same at all values of phi, provided they have the same values of theta and r. So it's symmetric with respect to the phi na direction, or the phi axis. So if you have azimuthal symmetry, your potential doesn't depend on phi, the azimuthal angle. So which means that we can just write separable solutions in r and theta. So our Laplace equation in spherical coordinates will just be reduced to two terms. So we do the same thing, the standard way of using separation of variables technique. We substitute v into the Laplace equation. Here our v is r times theta, and then we divide both sides by r theta, and you will get this result. So again, you have a function of r, and it's equal to some function of theta. And this could only mean one thing. This could mean that these functions are all equal to a constant. Here we will let our constant be equal to L times L plus 1 for reasons that will appear later. So you cross multiply r here, and this is your r equation, or the radial equation. So you cross multiply sine theta and theta here, and then this is our angular, the theta equation, or the angular equation. Okay, so I will no longer be exactly solving the solutions for this, because I will be, you just ask your mathematical physics instructor for the solutions to these radial and angular equations. So for the radial equations, the solutions are power functions. So it's actually a power r to the L and r to the negative L plus 1. Those are the solutions. And for the theta, or the angular equations, the solutions are actually, guess, it's Legendre polynomials, PL of cosine theta. So our x here is cosine theta. So PL of cosine theta. So combining these two solutions and taking into account that we have many possible solutions, because L can have values from 0, in integer values from 0, then this will be our general solution for any spherical systems with azimuthal symmetry. So you will take note that we only need to find two unknowns, AL and BL. So that one. So it's much easier to handle as compared to the Cartesian coordinate system. So L here starts from 0. Unlike in the Cartesian coordinate systems, that most of our solutions there, most of our dummy variables n, m, starts from 1, because if you start from 0, you will have v is equal to 0. But here, if you have L is equal to 0, you will not get v is equal to 0, the obvious or the trivial solution. So we will start from L is equal to 0 to infinity in integer values. So this is now the equation that we will use whenever we have azimuthal symmetry, spherical coordinates with azimuthal symmetry. So let's now have an example. So we have here a hollow sphere with variable surface potential. So from the statement alone, that it has a variable surface potential, so it's not an equipotential surface. So therefore, this could not be a conductor. So it's an insulator. So its potential actually depends on theta. The potential on the surface depends on the polar angle theta. So the polar angle is measured from the positive z-axis, from the north pole to the south pole. Okay. Then we are now asked to find the potential inside the sphere. Okay. So this is our general solution, of course. And in order to simplify or to convert this general solution to a specific solution to this problem, we need to have our boundary conditions first. No. So the boundary conditions for spherical coordinates are much easier to remember as compared to the Cartesian coordinates. Because if you have Cartesian coordinates, you usually have a box, and a box has 6 surfaces, so you have 6 boundaries. But for Cartesian coordinates, you usually only have 2 boundaries. If you're finding the potential inside, and it's just from r is equal to 0 to r is equal to capital R, or at the surface of the sphere. And if you're finding the potential outside, then it's from the surface of the sphere to infinity. So in this case, our first boundary condition will be as r approaches 0, v must be finite. So this is a generic boundary condition for spherical systems. So it must be finite. It must not blow up at r is equal to 0, because if the potential blows up, becomes infinite, then you will have something like a black hole effect within your sphere. You don't want that. So at the surface, at r is equal to capital R, at the radius of the sphere, the potential is given by this variable surface potential, v naught, as a function of theta. So we'll specify the value of this v naught later. So we apply boundary condition 1 to the first to equation 1, and in doing so, when r approaches 0 or r is equal to 0, this term here, when r approaches 0, it becomes 0. But this term here, r to the negative l plus 1, when r approaches 0, it's 1 over 0. So that actually approaches to infinity. But the boundary condition state that v must be finite, or v must not be equal to infinity. So in order to do that, we need to set our b sub else to be equal to 0, so that it will be finite. So in this case, the potential will actually be 0, and since 0 is a finite value, so we need to set our b else is equal to 0. So our b else will now be equal to 0, so this term is no longer needed in our general solution, and we are left with this solution. So it's now more simplified. So to solve for a sub L, we use the second boundary condition. So at r is equal to capital R, or at the surface, so r is capital R, the potential must be equal to v naught as a function of theta. Okay, so in the similar manner with the in the Cartesian coordinates, so we use Fourier's trick here. So in Fourier's trick, we multiply both sides, since these are Legendre polynomials. We multiply by Legendre polynomials. We multiply PL prime in both sides of the equation and integrate over dx, where our x is cosine theta. So integrate over d cosine theta. So this is the orthogonality condition or for Legendre functions. So PL of x, where x is cosine theta. So PL of cosine theta, PL prime of cosine theta, differential of cosine theta, evaluated from -1 to 1, is equal to 2 over 2l plus 1 delta LL prime. Again, we now have a Kronecker delta here. So this is 1 if L is equal to L prime, 0 if L is not equal to L prime. So we do that. So we multiply PL prime cosine theta both sides. So I just remove the as a function of cosine theta here for the both PL, so that our equation will be simplified. But actually you can write PL cosine theta, PL prime cosine theta here. But here I didn't remove the cosine theta, just to emphasize that PL is a function of cosine theta. So we multiply both sides by PL prime cosine theta and integrate over d cosine theta. So you don't need to expand this yet, because we need just to evaluate cosine theta from -1 to +1. And the answer of this is, of course, 2 over 2l plus 1 delta LL prime. In the similar manner, again, we have encountered this over and over again when we discuss about the separation of variables technique. Only one term in the summation will survive. The term where L is equal to L prime. So only one term will survive, AL. So you have AL r to the L, and this term is just 2 over 2L plus 1. So you can now solve for AL. So AL is just cross multiplying 2L plus 1 over 2, divide by r over L both sides, and this integral here. Again, we cannot evaluate the value of AL without evaluating this integral. And further, we cannot evaluate this integral if we are not given the exact value of V naught as a function of theta here. Now, suppose our V naught of theta here is k sine squared theta over 2. So we now have an exact value of V naught here. Now, whenever you encounter Legendre polynomials inside your integral, it's easier to convert the functions beside in the integrand, beside your Legendre polynomials, into Legendre polynomials and take advantage of the orthogonality relation. So this means that we must convert this potential here, V naught, in terms of the Legendre polynomials. And how will we do that? So first, to simplify this, we will use the relation of sine squared theta. Sine squared theta is 1 minus cosine 2 theta over 2. In this case, it's just 1 minus cosine theta over 2 because our theta is theta over 2. So that one. So we actually have k over 2, 1 minus cosine theta. Now, if you will recall, the first two Legendre polynomials, 1 is actually can be represented as P0. And x, in this case, our x is cosine theta. So meaning cosine theta can be represented by P1. P1 of cosine theta. So we can actually use that. So we replace 1 by P0 of x, or P0 of cosine theta. And cosine theta, which is our x, we replace it with P1 cosine theta. So basically 1 is P0 and cosine theta is P1. So we use this, substitute this to our integral here. So this integral becomes two terms, or we now have two integrals. The first integral will be an integral between P0 and PL, and the second integral will be an integral between P1 and PL. So this is the first integral between P0 and PL, and the second integral is between P1 and PL. And of course, we take advantage of the orthogonality condition or relation between Legendre polynomials. So this integral is just 2 over 2L plus 1 delta L 0, because L, the subscripts are L and 0, or 0 and L. And this one is just 2 over 2L plus 1 delta L 1. So this integral will only have a value of 2 over 2L plus 1 if L is equal to 0. Similarly, this integral will have a value of 2 over 2L plus 1 if L is equal to 1. So this means that these two integrals cannot have a non-zero value at the same time. One integral will be 0 and the other integral will be non-zero at one time. But you will notice here that there are only two possible values of L. L is equal to 0 and L is equal to 1. The rest, if L is equal to 2, for instance, if L is equal to 2, then this delta function becomes 0, this delta function becomes 0, and your A2, L is equal to 2, is 0. So this means that A2, A3, A4, A5, A6, anything not equal to 0 and not equal to 1 are all 0. So only two values of L are possible, meaning only two values of our constants AL are possible. You have when L is equal to 0, which is A0, which is just k over 2. So when L is equal to 0, this delta function is 0, and this delta function is equal to 1, and you will get k over 2. So when L is equal to 1, so this delta function is 0, because L here must be equal to 0. So since L is equal to 1, then this is 0, but this is equal to 1. Delta L1 is equal to 1, and you will get this value. So going back to our general solution, which is a summation, so only two terms will survive in the summation. L is equal to 0 and L is equal to 1. So L is equal to 0, that's the first term, and L is equal to 1. So we already know that P0 is just equal to 1 and P1 is just equal to cosine theta. And A naught, or say A0, is this one, A1 is this one. R to the 0 is 1, R to the power of 1 is R. So simplifying that, we get this potential. So this is the potential inside the sphere, and inside the sphere with a variable surface potential. So that's it for this problem. Now, how about we have the same problem, but now we are trying to find the potential outside the sphere and the same potential at the surface. So by the way, how do you explain this potential at the surface? Where is the maximum potential? So theta, when theta is equal to 0, that is the north, at the North Pole. So at this region here, that's theta is equal to 0. When theta is equal to 0, you will notice that this is 0. So there's no zero potential here. The same thing with theta is equal to when theta is equal to 0. So when theta is equal to pi, so you will get pi over 2, or 90 degrees. That's actually the maximum potential. So in this example, at theta is equal to 0, the potential here is 0, and theta is equal to pi, the potential here is maximum. So the only difference here are the boundary conditions. So the boundary condition is now from as r approaches infinity and at r is equal to r at the surface. So we still use the same general solution. We apply the boundary conditions to that general solution and we get this value. So this is the potential outside. So I will leave this as an exercise for you. So if you compare this with our previous result, the potential inside, so you will notice that these two potentials at r is equal to capital R will actually have the same value, k over 2, 1 minus cosine theta. So because potential is continuous even at the boundaries, so that means that the potential outside and the potential inside must approach to the same value at the boundary. And if you are trying to solve for the potential induced surface charge density at the boundary, then you use the discontinuity of the derivative of the potential. So the derivative of the potential outside minus the derivative potential inside times negative epsilon naught. So of course you need to evaluate this at the boundary. So take note, if you are trying to solve for the surface charge density, always evaluate it at the surface or at the boundary. So in this case, at r is equal to capital R. So you just take the derivative of this with respect to r, since r here is our normal to the surface, perpendicular to the surface na coordinate. So derivative of this with respect to r, derivative of this with respect to r, and evaluate at r is equal to capital R, and you will get this result. So this is now the surface charge density, surface charge distribution on our hollow insulating sphere. So if your surface is not an equipotential, so you will expect that its surface charge density will also not be uniform. In fact, it actually depends on your polar angle theta. Okay, so let's have another example here. So this is one of the more common examples in spherical coordinates. So suppose you have a uniform electric field and it's directed towards the positive z axis. So it's uniform, it's not bending or anything. Its magnitude is E naught, its direction is z hat. And suppose you place an uncharged metal sphere in a uniform electric field. So what do you think will happen? So I think you may have experienced this before in your basic electromagnetism. So since this is neutral, so the number of positive charges and the number of negative charges are equal. But since positive charges go along the direction of the field, they will be forced to move along the direction of the electric field until they reach the surface. So this is what happens to the positive charges. They move towards the direction of the field until they can no longer escape. They are now at the surface. Similarly, for negative charges, they are forced to move in the opposite direction of the field. So they will concentrate in the south pole here. So most of the positive charges will concentrate at the north pole area. So what will actually happen is, in the vicinity around your metal sphere, take note, this is a conducting sphere, the electric field inside is 0. The electric field will actually bend slightly in the vicinity of the sphere, but outside the sphere it continues to be straight. So you will notice that since there's now positive charges here, there's negative charges here, there will be actually an electric field inside from the positive charges to the negative charges, and that electric field will actually be the one canceling out the external electric field. Hence, the electric field inside becomes 0. So in this problem, we are asked to find the potential outside the sphere. So since this is a metal, a conductor, the electric field inside is 0, meaning the potential inside is constant, and we'll just assume that it's 0, since 0 is a constant potential. So we'll assume that the potential inside, electric field inside is 0, the potential inside is also 0 up to the surface. Okay. So before we can write actually our boundary conditions, we need to ask this question first. What happens when r approaches infinity? Because this is our condition. What happens when r approaches infinity? What happens to your potential actually? Take note, we have an external electric field here. So when r approaches infinity, so we are now trying to find the potential at infinity. So we cannot set our potential at infinity to be 0. So we are trying to find it because there's an external electric field. So we use the formula negative E dot dl, where our dl here is just dr, the r coordinate. So our reference point now, we are trying to find the potential at r where r approaches infinity, and our reference point now is the surface of the sphere. Now, at the surface of the sphere, the electric field there is 0 because technically that's still part of the inside of the sphere. So the electric field inside is at r, or at the surface of the sphere, is 0. So meaning at the reference point, E dot dr there is 0. The electric field is 0. So the only contribution will be at r, where r approaches infinity. So since this is just E dot dr, that product, so this is just E dot E dr cosine theta. And since the electric field is constant at r, where r is infinity, then this is what the electric field will approach to when r approaches infinity. So negative E naught r cosine theta. So the electric field at r is E naught z. The electric field at capital R at the surface is 0. So the lower limit evaluation corresponds to 0. So only the upper limit, negative E naught r cosine theta, where theta is the angle between E and R. So basically the polar angle, it's E, that's your z-axis, and that is your theta measured from the poles. So the boundary conditions now is when r approaches infinity, the potential will approach to this value here, negative E naught r cosine theta. And at the surface, or at the boundary, r is equal to capital R, the potential must be equal to 0. So we set it as a constant, and why not let it be 0 for easy calculation. Okay, we still use the same general solution for spherical systems with azimuthal symmetry. I will no longer be solving this problem, but it's just very easy. Actually, we'll find out that spherical separation of variables in spherical coordinates are much easier to solve as compared to Cartesian and cylindrical coordinates. So applying the boundary conditions, we can now solve for AL and BL, and we get this value. So of course, you will probably always use the Fourier streak. So in this case, the Fourier streak involves the orthogonality relation between Legendre polynomials. So this is the potential outside of the sphere. So you will notice when R, so let's try to check if our solution is correct. So when R approaches infinity, so this term becomes 0 or approaches to 0, and our value of the potential is negative E naught R cosine theta, which is our first boundary condition. And at R is equal to capital R, so at R is equal to capital R at the surface of the sphere, when this is capital R, so you have R cubed over R squared. So this is just R, and this is just also R. R is equal to capital R. R minus R is 0, so you have a 0 potential. So the second boundary condition is satisfied. So always do that, please. When you're calculating the potential, always check your answers, cross-check your answers with the boundary conditions. Because if it satisfies the boundary condition, then you are probably correct, or you are mostly correct. Of course, if you are asked to find the potential at the surface, so since the potential inside is just 0, so there's no second term here. So, but in the general equation for this, it's partial of V outside minus partial of V inside. But since the partial of V inside is just 0, so we're just left with this one-term equation. So if you get the derivative with respect to the normal coordinate, which is R, normal to the surface or perpendicular to the surface, that is actually the R direction, R hat direction, and you get this one, 3 epsilon naught. Okay, so it depends on the polar angle theta. So when theta is from 0 to within 0 and 90 degrees, the value of that cosine is positive. So from 0 to 90 degrees, the value of that is positive. But when theta is between 90 degrees and 180 degrees, or pi over 2 to pi, so this angle pi over 2 to pi, the value of that cosine is actually negative. So that explains this one. So from 0 to pi over 2, it's positive. From pi over 2 to pi, it's negative. So that explains the charge distribution here. So you will get a positive charge on the upper hemisphere and a negative charge distribution on the lower hemisphere. Okay, I will actually not be discussing about the separation of variables in cylindrical coordinates because it's just the same method. It's just the same process actually. So this is our Laplace equation in cylindrical coordinates, and again we will assume that the potential has a symmetry along, in this case, along the z axis. So most of the cylinders are aligned along its length are actually aligned most of the time along the z axis. So you have a symmetry along the z axis. So which means that your potential will just depend on the two-dimensional radius s and the azimuthal angle phi. And you just your Laplace equation will just be reduced into a two-dimensional partial differential equation. So using the same steps, you substitute v, you divide both sides by s and phi, and you will get this result. So you will notice that even though this is just for a two-dimensional cylindrical coordinate problems, a separation of variables in cylindrical coordinate problem, but the general solution is very, very long. So it's actually quite tedious to solve the Laplace equation in cylindrical coordinates, or to have a problem with cylindrical symmetry and solve the potential using separation of variables in cylindrical coordinates. So it's actually not practical to have a problem in cylindrical coordinates in an actual exam, for instance, where there is a constraint or a time limit. So don't worry, I will not be giving you problems in cylindrical coordinates during an exam, but maybe on your problem set, because you have a lot of time. You can sorry, you can have the time is unlimited when you are solving, when or there's no time constraint for problem sets or assignments, or maybe there is, but it's actually pretty long. So that's it for actually, for the derivation of this general solution. You see problem 3.22 in our textbook, the Classical Electrodynamics by Griffiths. So that's it for the separation of variables. So we will have our last topic, which is the last technique in finding the potential given the boundary conditions and given the charge distributions. It will be on multipole expansion. So you can actually expand the potential in terms of monopoles, dipoles, quadrupoles, octupoles, and so on. So that will be our last topic for this chapter. So for this lesson, that's it for this lesson, and I will see you next meeting. Lars was quiet.